A foundation model is a large-scale AI model trained on a vast and diverse dataset, typically using self-supervised learning at scale, such that it can be adapted or fine-tuned to a wide range of downstream tasks. Unlike traditional AI, which was designed for a single specific purpose, like translating English to French, a foundation model is designed to capture a broad representation of information that serves as a functional starting point for many different applications. To understand these models, we must look at three primary pillars: scale, emergence, and homogenization. First, let's talk about scale. Foundation models are defined by the sheer volume of data and computational power used during their creation. They ingest trillions of tokens from the internet, books, and code. They contain billions of parameters that allow the model to map complex relationships within that data. In the past, if you wanted a model for sentiment analysis and another for summarization, you would build two different architectures. Today, we use the same foundation model for both. This homogenization means that a single methodological approach, usually the transformer architecture, now powers almost all natural language processing tasks. As these models grow in size, they begin to exhibit emergent properties. This means they develop the ability to perform tasks that were not explicitly programmed to do, such as basic reasoning and code generation, simply by learning the statistical patterns inherent in the massive datasets they were exposed to. A foundation model exists in two distinct phases. Phase 1 is pre-training. The model is trained on a massive, unlabeled dataset. During this stage, it learns the structure of language, logic, and world knowledge. It is not yet good at any specific task. It is simply a statistical engine that predicts the next most likely word in a sequence. Phase 2 is adaptation. Once the foundation is laid, researchers adapt the model. This is done through fine-tuning, which is training the model further on a smaller, high-quality dataset for a specific task, like medical diagnosis. And the other is prompt engineering, providing specific instructions to guide the model's existing knowledge towards a desired output. So why the term foundation? The term, popularized by Stanford Institute for Human-Centered AI, HAI, is an architectural metaphor. Just as a building's foundation provides the stability and shape for whatever structure is built on top of it, whether it's a house, a school, and a hospital, a foundation model provides the underlying intelligence for thousands of specialized applications. If the foundation is biased or flawed, every application built on top of it will inherit those flaws. The foundation is built using self-supervised learning. Unlike traditional supervised learning, which requires humans to label data, SSL allows the model to create its own labels from raw data. Most foundation models use a causal language modeling objective. The model is given a sequence of tokens and tasked with predicting the next token. So the goal is to minimize the cross-entropy loss, a mathematical measure of how surprised the model is by the actual next word. By predicting the next word trillions of times, the model implicitly learns grammar, logic, and even cultural nuances. Research has shown that the performance of these models follows predictable scaling laws. As we increase three specific variables, the model's error/loss decreases in a power law relationship, where n is the number of parameters, d is the amount of training data, and c is the total floating point operations. The definition of a foundation model has expanded beyond text. We now see native multimodal foundations. In earlier iterations, researchers would glue a vision model to a language model. Modern foundation models are trained on text, images, audio, and video simultaneously in a shared latent space. This allows the model to understand that the word apple and an image of red fruit represent the same underlying concept. A critical area of ongoing research is whether the foundation models truly develop new abilities or if they are simply getting better at statistical matching. Some tasks like multi-step math show zero success until a model reaches a certain size, at which point accuracy jumps to 80%. Many researchers argue that this emergence is often an artifact of how we measure success. If you use all or nothing grading, it looks like a sudden jump. If you give partial credit for correct steps, the improvement often looks like a smooth, predictable curve. The most recent evolution in foundation models is the shift from bigger training to longer thinking. Standard models provide an answer instantly. New architectures allow the foundation models to use inference time compute. This means the model can reason through a problem using chain of thought or internal search before delivering an answer. In this paradigm, the foundation isn't just a static database of knowledge, it is a dynamic processing engine. While general-purpose models like GPT or Gemini are famous, the research community is increasingly focusing on domain-specific foundations. Like biology, in which models trained on genomic sequences and protein structures, time series, models trained on financial or industrial sensor data to predict future trends, or code, models optimized purely for the logic and syntax of programming languages. Historically, a foundation model's intelligence was determined by its training time compute, how much it learned before you ever talk to it. Today, researchers are focusing on inference time compute. Instead of the model giving a gut reaction, it is now designed to think before it speaks. This is achieved through search and optimization. The model explores multiple possible answers and evaluates which one is most logically sound. Then we have chain of thought internalization. The model is trained to simulate a step-by-step reasoning process. We used to scale the model size n. Now, we scale the time the model spends processing a single query. This has led to a new scaling law where accuracy continues to improve as you allow the model more thought time during inference. One of the greatest challenges in AI research has been the black box problem. We knew foundation models worked, but not how. A major development in the last year is the use of sparse autoencoders to decompose the model's internal activations. Researchers discovered that models store information in superposition. This means a single neuron in the model might represent several unrelated concepts, example the Eiffel Tower, Python code, and the color purple. By training a separate, much wider interpretability model the sparse encoder or autoencoder on the foundation model's internal layers, researchers can now disentangle these concepts. This allows us to identify exactly where deception or bias is stored. Turned off specific behaviors like the ability to generate toxic content without retraining the entire model. We are moving past models that only understand language to models that understand physics. These are known as world foundation models. While a standard LLM learns the probability that the ball fell will be followed by to the ground, a world model learns the latent physics of that event. They understand 3D relationships and object permanence. They can simulate what happens if I push this glass off the table in a latent visual space. This is the foundation for the next generation of robotics. Instead of training a model for one specific factory, we give it a world foundation that allows it to navigate any physical environment. Finally, we are seeing the rise of agentic foundations. A traditional foundational model is passive. It waits for a prompt. An agentic foundation is designed to be active, maintaining a long-term state across different sessions. The model can autonomously decide to use a calculator, a web browser, or a GitHub repository, decomposing a complex goal into smaller executable subtasks. A raw foundation model is often unfiltered and unhelpful. To make it useful, we apply a post-training phase. This is the process of aligning the model's high-dimensional statistical representations with human preferences and safety constraints. First, let's talk about RLHF, also known as reinforcement learning from human feedback. We use a reward model to score the model's outputs. The model then updates its parameters to maximize that score. Next, we have DPO, which is direct preference optimization, a more mathematically stable approach where the model directly learns to distinguish between a preferred and a rejected response without needing a separate reward model. And then we have safety guardrails. We train refusal behaviors to ensure the foundation model does not assist in high-risk activities, for example, things like chemical weapon synthesis. So one of the most significant shifts in the recent research is the use of sparse autoencoders. For years, the internal workings of foundation models were a black box. We are now successfully disentangling these neural networks. In a standard foundation model, a single neuron might be polysemantic, meaning it fires for multiple unrelated things like the Golden Gate Bridge and Python code. By applying sparse autoencoders, we can extract millions of sparse features that are monosemantic. This allows us to find the exact direction in the model's brain that represents a specific concept, such as honesty, deception, or medical knowledge. This allows for feature steering. Instead of prompting a model to be more creative, we can manually dial up the internal creative feature by modifying the model's activations in real time. While the large in LLM was the focus for years, the current research trend is towards small language models and distillation. In model distillation, we use a massive teacher model like Gamma 3 to supervise the training of a student model. The student learns to mimic the teacher's reasoning but with 1/100th of the parameters. In quantization, we reduce the precision of the model's weights, example from 16-bit to 4-bit or even 1.5-bit. This allows foundation models to run on consumer-grade hardware or edge devices while maintaining near-frontier performance. The most advanced definition of a foundation model today is its ability to serve as the central controller for autonomous agents. A foundation model is no longer just a chatbot. It is the planner in a larger system. The model uses tool use or function calling to interact with the world. First, it perceives the user's intent. Second, it plans a series of steps. Third, it executes actions by calling external APIs like searching GitHub, running code, or updating a database. And lastly, it self-corrects by observing the results of those actions. This makes the foundation model the operating system for AI agents. The traditional foundation model was largely a System 1 processor. It relied on fast, intuitive next token prediction. Modern research has introduced System 2 capabilities, where the foundation acts as a reasoning engine. Rather than relying solely on human label examples, researchers now use pure reinforcement learning to incentivize the model to think. The model is given a complex problem and receives a reward only for a correct final answer. This process encourages the emergence of hidden reasoning steps where the model learns to self-correct, backtrack, and verify its own logic before outputting a final response. In this framework, the foundation is no longer just a database of knowledge. It is a probabilistic search algorithm that explores multiple solution paths in real time. As models become more autonomous, the method of aligning them with human values has shifted from manual labeling to constitutional AI or reinforcement learning from AI feedback. A researcher provides a small set of natural language principles. A separate critic model evaluates the foundation model's drafts against these principles. Techniques like direct preference optimization or DPO allow the model to adjust its internal weights to favor constitutional responses without the need for a complex reward model. This creates a self-improving foundation that can scale its safety protocols faster than human researchers could manually audit them. While the transformer architecture is the standard, further research is exploring alternative architectures to solve the O n to the power 2 complexity of long context windows. First, let's talk about state space models like Mamba. These models process data linearly, allowing for nearly infinite context lengths without the exponential memory cost of traditional attention. Next, we can talk about liquid neural networks. These are inspired by the nervous systems of smaller organisms. These models feature liquid parameters that change based on the input they receive. They are exceptionally efficient for time series foundations like robotics or high-frequency financial data. A large action model is a foundation model that has been fine-tuned to understand and navigate user interfaces. Instead of just telling you how to book a flight, a large action model-based foundation can, first of all, understand the goal or the intent. Second, it can parse the visual elements of a website. Next, it executes the clicks and keystrokes required to complete the task. For a developer like yourself, this represents a move from building chat apps to building autonomous agents that interact directly with the GitHub API, terminal environments, and cloud infrastructure.